Howdy 216ers, this is Professor Kaufman, and this video will take you through the ropes on Project 2. You can see from the project specification that you're up against three separate problems, and they are distinct from each other. There isn't any interlinking this time, so theoretically you could take them in any order. The third problem is probably the most familiar. It's just an applications level programming exercise to create a data structure and a little interactive loop to manage it. But it's probably a bit longer than the others. Whereas the credit you'd earn in problem two comes just from exercising the debugger, as we'll see. And problem one, you write a few minimal functions. However, they'll require you to do some bit level manipulation, which is new and interesting. So take them in an order that you think is appropriate. But the first two are probably shorter than the third one. Make sure to leave enough time at the end for that. There is a note on the difficulty that it's perhaps a bit more challenging because you have three separate things to go on about there. And the only update as of the recording of this video is that I inadvertently described the trees that are in here as hash maps. Sometimes we use hash data structures rather than binary search trees, but we'll get to that when we get there. All right, as is usually the case, there's some setup involved, a code pack that we'll download and set up in just a second, but a manifest for what's included in that and also what you'll need to create yourself is present in the spec over here. This table of stuff is one that you probably don't need to look at too much, except to note that in the first problem, you'll need to create this important clock update.c file, but there's an outline of the functions that should be in it down yonder just a little bit. And as well, in the third problem, you'll have to create two functions, or two files rather, tree map funcs and tree map main, where you'll put your utility functions and main routine respectively. Other than that, most of the rest of the data is provided, including a little input file that you'll edit, which has some preliminary information in it for problem two. Okay, let's dive into the problems themselves because the testing regime and all that is about the same. The first problem puts you in an embedded programming environment, wherein, this is often done in C, you're actually going to control a physical device of some sorts, a dumb little digital clock. Now, before we get to any of the code and setup or anything, I'm going to scroll down and show you pictures because pictures can summarize very well. In this device, there'll be some ability to control a display, and that'll be central to the problem. The display is a bunch of little LCD panels. Here's one of those panels that's not lit up. Here's another one that is lit up. Whether or not it is activated and so darkened in to show something or inactive, so showing blank basically, is dictated by individual bits. And you can see this display then, each of the little panels is labeled with a number, and that corresponds to a bit position. Up here is, I'm supposed to do lab work soon, no matter. Up here are 20, actually 30 different bits in a sequence that show, if you were to arrange bits in this pattern, this is what would show on the LCD panel display for the clock. And if you sort of roughly look at it, it looks 8:39 in the PM because it's evening wherever this is. Now the 9 is showed here because a certain set of bits have ones in them, but there's one absent. It's at bit position 4. You can see that up here in the little diagram. And the basic pattern of which of the bits lights up the top panel versus this top left panel versus this top right panel, that's the same across each of these digits. We'll get to that pattern somewhat. So in order to show this, if it actually were 8:39 p.m., you'd want to arrange some series of bits to look like the following. And since it's close to 32 bits, like this could be just an integer that is at least represented as an integer in a C program that way. Now, the 9 that you see here, it has nothing to do with, like, this is not binary 9 and 2's complement or any other encoding. This is just a series of turn a certain light on, turn a certain light on, make sure this light is off, and that will show some visually appealing information. So the bits themselves don't have a meaning except when put in the context of, like, I'm attached to light bulbs. And it's not uncommon for embedded programming to have features like this. Turn this electrical signal on this pin for the processor, and that will turn an associated light on or activate a motor or move something around. To that end, establishing some sort of a bit pattern that looks like this is a good skill to use and easily done in C using a series of bit level operations. Now, why 8:39 p.m.? Well, there'll be another part of the processor that's attached to some sensor or other bit of hardware that keeps time. that'll be exposed within the C program itself as a global variable, so clock time port in this case. And this will measure some unit of elapsed time since the beginning of the day. This time it'll be in units of 1/16th of a second. So if you divided this number by 16, it's some number of seconds since the beginning of the day. So if I divided by 16 and I saw a 0, we must be at midnight because that's the very beginning of the day there. It's not uncommon then within an embedded program setting for the little microprocessors to be attached to various things that are then exposed within programs as global C variables. But what this really corresponds to is some mechanical, physical device that's doing the timekeeping. In this case, it's probably a real-time clock of some kind, but we don't have time to go into what that means exactly. So by manipulating then, grabbing out this clock time port and then doing some arithmetic on it, you can figure out this is what time of day is. It's 8:39 p.m. And then by further manipulating another global variable, this clock display port, this is where if you put in this specific sequence of ones and zeros in the 32-bit integer, it'll be attached to external parts of the processor that actually light up the display over here. Below this is another example of if we were at 12:05 p.m. Or a.m. rather, so very close to the a.m. Is another bit pattern over here. You can see one of the lights at the end is attached to this a.m. indicator versus there's a separate light here, the 29th, that's attached to p.m. over here. It's fairly common for little digital display devices. Hopefully you've seen a digital clock like this. To that end, the pattern that you want to sort of figure out as you're figuring out like where to put these bit patterns over is just to recognize each digit can follow the same basic pattern. So if I was looking to establish a time that's like 4:15 p.m. or something like that, I want to maybe start with the 4 and say, here's a bit pattern that would display a 4. But then take this pattern and shift it over so that it's in this position where the 8's at. And the shifting part is literally a left shift operation in C. Then combine that with a 1 in a different position, possibly also shifted from the 0th spot over here to the 7th spot as a starting point, and that would plop a 1 here, and then take the pattern for 5 and combine that, hint, hint, a bitwise OR, with the other things, but not shifted this time, so it's over here, and maybe slap a 1 over here at the ends because it's 4:15 p.m. That's the essence of what this is to exploit the fact that each digit has the same basic bit pattern, and as you shift them over, you can create a series of sort of on-offs that would display things. Now, in some cases, in some problem settings, you might need to display other things like letters E or negative signs. That doesn't have a place with our clock business here, so you don't need to pay much mind to this other part over here. If we scroll down a little ways then, the basic functionality of this will be divided into 3 functions. They are in turn this set TOD from ports, and so in a minute we'll copy some of this into a source C file to get started, a set display from TOD, and then a clock update function. In series, the essence of the first function, set TOD from ports, is to grab out this global clock time port variable, do some calculations on it to determine, based on its value, it's 8:39 p.m., and then fill that time into this little struct here, TOD, it's described here. It has the raw number of seconds since the beginning of the day, but then subdivided into a number of seconds, minutes, the hours, and then whether it's in the AM or PM. And so this is a fairly elementary function. It will just do some arithmetic and fill in some struct fields, so no major issues there. There are a couple of constraints. So for instance, you'd want to use only integer operations. That's shifts, ands, ors, multiplies, divides, etc., but no floating point stuff having to do with like rounding or fractional parts or anything like that. And that's on account of cheap microprocessors that might go into a digital clock that don't actually have a floating point unit, so couldn't handle any IEEE 754 formatted floating point numbers. Staying away from that in your C program, then make sure that it'll work on the target microprocessor. There's also a sort of constraint on you must limit the complexity of your code as much as possible. And that's on account of you're going to eventually rewrite this function in assembly. Take the C plan that you laid out and plop it down in assembly. Since each line of C might translate to 1 to 5 lines of assembly code, it will behoove you greatly to limit the complexity in your C plan as much as possible, because that'll make it easier to translate into assembly. So avoid things like there's no need for loops or deeply nested conditionals here. If you go 2 levels deep in a nested conditional, try to rethink it, see if you can figure out a more flat single conditional that will do the trick there. As you'll thank your future self will thank you later on for doing so, as it'll be much easier then to translate into assembly. There's one other constraint that's sort of making this, that this amounts that's the sort of raw value for the global variable, this time, or is it a clock time port here? You'll need to divide that by 16 using a shift operation and fish out both the quotient and remainder from that. You'll maybe do a little bit of research to figure that part out, but there's a bit of style points for doing it that way. And that's to avoid the cumbersome division instruction. Doesn't make a lot of sense at the C level right now, but illustrate your ability to do so, knowing that later on, this will actually be easier to do in assembly if you do it with a shift. The second function would take one of those structs and then calculate, this is what the display is going to look like. So it's the process of taking something that's like, oh, it's 8:39 and 15 seconds into the day in the PM, and then constructing this display up here. Plopping down the hours digit is an 8, so I'll put this thing here, shift it over to this spot, and we're good to go. Taking and finding that the minutes is, or the tens of minutes is 3, and so I'll plop that down here, and the single digits of the minutes is 9, so plop that on here unshifted, and then putting an AM PM over here. You can see that the layout here is directly reflective of that. That a couple of digits might come from the hours. If you've got 10 o'clock, 11 o'clock, 12 o'clock, otherwise it'd be a single digit. A couple will come from this time minutes. The seconds we don't care about, so there's no rounding on that. And then the AM PM indicator here, that will indicate whether to light up one of these 2 lights, either the AM or the PM. So this is the function that will probably occupy you for the most of this problem, because it involves directly using these bit shift operations to construct a certain bit pattern that looks like this and will display something that looks like this when embedded in that device. Finally, then down here, there's a clock update function that calls the previous 2 functions, checks that their results are okay, and then proceeds to the next one if it's all well. Generally, there's no need to allocate any memory, so don't bother mallocing anything in here. And plan to spend most of your time on this middle function to get it right. There are a couple of hints in here. For instance, it's extremely useful to have some sort of an array that has, oh, if I'm supposed to put a 1 on the screen, then I'll have an array that says in my 1th spot, this bit pattern appears. That makes it really easy when you divide something and say one of the digits is 1. I'll go to the 1th entry in this array, fish out this bit pattern, and plop that down in a broader context, like in here by shifting or something like that. So most sane solutions are going to have an array that looks kind of like this thing, and the 0 slot, this bit pattern, the 1 slot looks like this thing, the 2 slot, and so forth. And maybe I'll sort of demonstrate how one might go about arranging something like that shortly. There are a few other sort of hints in here. For instance, there's a little simulator that you can do, and some sample runs of this down here. So since we don't have the actual device, we can do things like, okay, after you compile and you finish at least parts of your clock update.c over here, you can run clock main and feed in a sensor value for this clock time port. So 0 would be the very beginning of the day, so nothing has happened since then. So 0 seconds, which should translate then via the first function to the struct values. Oh, the hours is 12, the minutes is 0, the seconds is 0, and the AM PM is 1. So simulated time is 12 a.m., a dead midnight. And if all is correct, I'll take this part right here, the 0 minutes thing, and fish out a couple zeros to plop down here and here for the display port. And then the 1, 2, that would be a 2 right here and a 1 right here. And the simulator will then display something that looks sort of like this thing in order to indicate that's the time as it would appear on the clock display. So now it looks all right here. Now, this is correct behavior, and we'll start out with some incorrect behavior very shortly, but no matter there. Okay, I think that's enough preamble on this problem. Let's actually do just a little bit of coding on it. For that, I'll grab the code pack here. So copy the link address, jump over to my editor, and open up a shell. I'll wget this thing. So it's in here. I got my P2 code, so I'll unzip the provided code pack and then change in there. If I have a look, you can see most of the files are provided here, but missing is there's no clock update up here. That needs to be created. So let's do so. I'll make a new file, clock update.c. You can see the file name down over here. Punch enter. Some obvious things to include. Well, there's a header file in here that has information about the structs and so forth. And so I'm just going to blithely plop that one down. Include clock.h. I think that's the only one that you'll need for this file. That might be wrong. You might have to pound include some like stdios or some such in the event that you're doing things like printing debug message or something like that. But we could also use function prototypes at this point. So let me come down here to clockupdates.c. We're going to need these three functions. The set TOD from ports. Grab that thing here. Gonna need the set display from TOD, like that. And then the clock update. Okay, so I got stuff out there on that. Take this thing and I move it down here as it's a little bit easier to work on. This is supposed to return an int. I haven't even bothered to read whether or not it's supposed to return a good int, bad int. What does it return on success and failure? I'm going to return 1 for now. And similarly, copy that over here for the other definitions, because that's really all that's needed to get us underway here. Okay, I think that should do it for now. Now, if all goes well, and I'm correct, then I should be able to type make or make test prob1 and actually run the large number of tests associated with this problem. Let's check that in a shell over here. So make test, actually, but I'm going to try make prob2, which will try to build the programs associated with problem2. Oh yeah, oh no, that's not problem1 rather. Okay, so that worked out just great. Problem2 has all the code provided. We'll get to that in a second. But down here, you can see the clock update.c that I provided is totally fine, and everything else built just fine here. So let's maybe give a test run. So test prob1. And it looks like a whole lot of fail on the screen here, but that's sort of expected because we haven't even done anything yet. Oh, look at that. It actually passed some tests, and I think these are the error versions that didn't bother anything new, just reported like problems on it. And so no matter there. Now, you'll note down here that there are 40 tests run, but each is only worth a half point. So I'm getting some fractional values there. Pay that no mind, seek to sort of pass all of these over here. And we'd be at the stage here then when I'd look sort of at this, okay, set to your reports, so I check the initialized set, etc., blah, blah, blah. I'd want to move ahead and try to get something sort of on the screen that looks correct for the functional requirements of this function. I don't want to spend any time on this one right now, the set TOD from ports, because that's really easy. Grab some global variables, which are provided to you, do some arithmetic on, set some fields there. Instead, I'm going to change my code so that this thing returns a success. And I'm actually going to futz for just a second with this second one to show what's on here. So I'm going to return a 0 there. Not going to put anything else in here, because first I want to show if you were going to experiment with this thing interactively, do a make prob2, prob1, then you could run this clock main over here. And by default, if you provide no arguments, it actually pick the current time of day over here. And the main will actually set the sensor to be whatever values associated with the current time of day. Let me grab this value and run it. over here. I'm just going to add like a 23 onto it or something like that. And so you see the display over here, it actually doesn't show anything. So if I run it again, it's there. Let's futz with that just a little bit because this is the essence of it. There's this global variable that's mentioned down, well, somewhere around here for that. The clock time port is the one you're supposed to read, and clock display port, that's the one you're supposed to write. Now I'm going to do something that's a little bit wrong right now. I'm just going to directly set this global variable here, the clock display port, to do some things in here. Generally, this is not what you should do in this function, but it'll let us see a couple things here. So if I set this thing to be, and let me just pick a binary constant. Here's 0, 1, 0, 0, like this, something like that. I have no idea if that's enough bits or not, but there's some ones in there, which should then turn on the display in the simulator. So let me come back over to the shell. I'll do a make prob1 here. It'll recompile. And if I run this thing again, then you see gobbledygook over here. The top left bar, bottom right bar here, something like that. One other thing I could potentially do here that's interesting is let me take my clock display port. One moment. So if I take this global variable and modify it in the following way, let it equal to itself, and maybe I'll shift a 1 forward on, let me shift a 1 over by 29 bits. 29 because in looking at the diagram over here, the 29th bit here is tied to this little PM light. Then if all is correct, this should turn on. I'll have to recompile it and rerun it. This should turn on, hey, the PM. Well, I guess it's on the right in this rather than the left over there, but no matter. And ostensibly, if you did the same thing with the 28th bit here, I'll recompile and rerun. You can see, oh, AM and PM simultaneously there. Now, none of this is desirable. And the actual specification of this function is you don't mess with this global variable. Someone is going to pass you a pointer to an integer that you should set to a pattern that's like this combined with a shift over there. So don't play with clock display port here. Instead, make use of display. I do this here simply to illustrate the simulator can be a powerful tool aside from the test cases as you'd want to experiment and interrogate what your code is up to there. And ultimately, some of the test cases make use of that little simulator to see what's happening. At any rate, take some time to fill in the correct values for the time of day in this little TOD struct in the first function, and then move on to take and extract those and figure out I should put a 1 here and a 5 here and a 12 here and so forth in order to create that display port. Just make use of star display instead in that case rather than clock display port. And finally, in the last function, like tie those two together and do some little error checking if things go awry. Problem 1, embedded programming in the form of low-level clock. Second problem is quite different in nature and asks you to make use of the debugger. So it'll center around a little program called Puzzlebox. The source code for that is provided in here. So if you look in the project's directory, there's a puzzlebox.c. There's some instructions up top for this, and we'll exercise those instructions in just a little while. There's a bunch of stuff in here, but largely the structure of the program is divided between a main, and the main subsequently calls a bunch of phases. Your objective is to satisfy the requirements of each of these phases, which relate to some kind of input needs to come into the program, and then that input is interrogated through various ways. So you spend a lot of time looking at the source, maybe not in here, but of those phases, but at some point in phases. And let me sort of skate down just a little ways to find one of these because there's like a phase 1 right here. Now, if you're just looking at source code of this thing, you'll see that there's some input that comes in. This will come out of a file that we set up. And then some bit of arithmetic is done here that is intentionally obscure. So figuring out, okay, if I plop some values down in here and then try to do the math, ostensibly, you could do this in your head and certainly with a calculator assist, but it's a little bit difficult, particularly because this hash value is not like well known to you. Instead, the point of this kind of a program, this exercise rather, is to get you to make use of the debugger, to set breakpoints within here and interrogate program values to figure out, oh, this is the next step. This is how I should adjust my input here. And so we'll do that very shortly. If you were to run this puzzle box like as is right now, you'd probably get, let's see, I think I did the make prob 2 part here. So I've got a puzzle box around. It'll complain first that you need to provide an input file for it. There is a little input.txt in here, which is reminiscent of what you'll have done in this week's lab with a phase 3, which happens to be the exact same phase 3 that's in here right now. But if I run puzzle box on this thing, then the first thing it'll say is like, there's a complaint about the format of this. And let's open up input.txt to see this directory ID that's right here is actually supposed to be your directory ID. Traditionally, when I was an undergrad, I was cough0095. This will be a what is like 3 to 8 character string that's your unique handle at UMD. That's the first part of your email address. And what this is used to do is to create a bit of a randomized experience. So the numbers that you'll need to enter for the remainder of this input file are somewhat different than your neighbors. That enables two things. One, you'll have a somewhat unique experience, but two, it's easy to collaborate with folks as your specific answers won't work for them. So you can discuss what's the essence of what this phase is trying to accomplish. So feel free to chat your neighbors up about that part. Now, having made that adjustment, if I run this thing again, PuzzleBox will be slightly happier and like actually initiate a phase, but the numbers I punched in here, 1, 2, 3, are not satisfying that. So the step to make this easier then is to make use of GDB to stop time to look at program values and get deeper insight into what's happening. Since GDB tends to not like to run in my like Emacs subshells, let me fire up a proper terminal here to have at this one. I'll be over here. I'll maybe increase the size a little bit. Listing. I want to here fire up GDB looking at PuzzleBox and then run this input.txt under it. So the syntax for that will be GDB, that's the command. Tend to want the text user interface. That's a more ergonomic setup, although there are a few trade-offs there. The program that I want to run, PuzzleBox, and I might try to put arguments here, but GDB doesn't actually honor them. That has a different way for doing that. So I'll punch enter at this point, push enter, and you'll see the text user interface for this thing where the source code is up top for this is what's in puzzlebox.c. And down below is a little command console that allows me to do things. Now, most of my attention will be focusing on phases, but let's start first by setting a breakpoint at the main function. There's several ways to set breakpoints, and I encourage you to read the GDB guide on that. But one of them is via function name, and right now main is like present here, but within this thing, so I can punch enter and I'll set a breakpoint there. If I run at this point, I'll probably get some errors at some point because I want to set up the command line arguments. There are a couple ways to do that. I can do a set args to be input.txt, and the other common is just to run and then plop down input.txt here. I'll favor the latter right now because it's what's on the screen. My stupid system is always wanting to download some debug stuff, but if yours doesn't, no matter. Up top, then, you'll see we've hit the first breakpoint, which is the first line of main. As I type next here to move ahead, you'll see one of the irritating features of the text user interface is that this gets printed. It gets printed in the console down here, but that tears the screen just a little bit. So if I type next again, then things are getting weirder and weirder here. So you'll commonly then start punching the keystroke Control L to redraw the screen, which will eliminate the printed outputs and restore the sort of user interface input over here. So keep that one in mind. You'll be probably punching Control L a lot as things happen here. Now, I don't really care about main that much, so I'm going to delete the breakpoint there. Just typing delete will delete all of them. And the real breakpoint that I want to set is at this phase 01. Now I'll pause at this point because, like many tools, GDB is extremely cognizant of programmer convenience. And so if I press tab at this point, it will autocomplete as much as it can that there's a bunch of functions named phase. And if I press tab a couple more times, it'll say these are all the phase functions. And so look for tab completion within GDB, at least its 2E interface here. I'm interested in phase 1 because I haven't made any farther than that at this point. So I'll break at that point and then use the continue GDB command to say keep executing until you hit another breakpoint. Notice the screen tearing. I'll press Control L and that'll reset things and see hit the first breakpoint here at the beginning of phase 1. So if I punch now next, A is now in scope in terms of the scopes established in the programming language. So I can print it out. It is a 1. And if you're curious where the 1 comes from, well, it's right here. That's the 1 that I have as the first input there. If I next a couple more times, and there are lots of shortcuts in GDB it's useful to know about, just N is next. And if I press Enter, it'll rerun the last command so I can sort of cycle through on those. I can now print out, here's B, it's 2, and print out C, it's 3, and so forth. Now, the real thing that is of some interest is this hash value. This is going to be based on that unique identifier, my directory ID that I put in. And it's this big god-awful like thing. Certainly, I could pull out a calculator and add 41, or sort of add or do modulo remainder of 41 of this thing and add it on to the A, or I could just type next and print out what is A now. A is now 36. And analyzing the condition that's required here, A is 36, so it won't be less than B that we saw earlier was 2. And so we're already failing this condition here. To that end, we do have some insight, though, about what we might modify the variables to be. So if I was interested in passing this condition, I'd have to make B bigger than 36. And so I'll skate over here. A starts as 1, but it has something added onto it, so it becomes 36. Let's make this 37, and so we're good there. Now, if you're entrepreneurial, but you might look ahead a little bit and say B has to be bigger than C. It is. So C is 3 right now. And the last condition, A has to be less than C. And C right now is 3, but A becomes 36. So A is not less than that. Okay, so we might have just. It seems A has to be less than C, so let's make C 37. B has to be bigger than that, so let's make it 38. And then we'll see where we come down. So this is pot shots, but that's fine. The inputs have changed, and so I'll need to rerun the program to get to this point. I'm really only interested in this spot here by line 277. So I'll use the convention. I'm going to delete all of the breakpoints. You can see the B over here like went away at the beginning of this. I'm just going to type break. Well, we'll set a breakpoint at my current line. Rerun from the beginning. And now I'm exactly where I want it to be, which is at this spot. Let's print out A. It's 36. Print out B. It's 38. Print out C. That's 37. So as I next at this point, hey, I'm going to return. And that will avoid missing this conditional and falling into the failure part, which is a loss of points there. So I'll type next again. This is going to complete that function, pop back up to main, and add some points onto my total. So over here, if I fired up the shell once more and ran, here's puzzle box input. So I guess it's a sort of dual display over here. You can see, I've actually got 3 out of 30 points now because I passed the first phase there. I'm also getting some warnings because phase 2 wants more inputs and I'm out of them over here. So it'd be a good idea to maybe plop some more things down here like A, B, C, or 1, 2, 3, and examine the next phase either in the debugger or in the source code in order to determine what's the format needed for this. Is it strings? Is it integers? Is it single characters, etc.? One minor note, the next command in GDB will move to the next source line, and that's distinguished from the step command, which will step into functions. Printf was a function, and I have no reason to go into the source code for printf, so next is appropriate. Phase 2 is a function I'm interested in, though, so step will take me within it. So jump step into it in that case. And you can see over here, each of the inputs for phase 2, they're attempting to convert them to integers. And so integer values like 1, 2, 3 wouldn't be a bad place to start. You note down here a good friend goto, and so you'll maybe want to review syntax for that and what it means out there. But I'll leave the rest of the debugging exercise to you. The challenge increases as you move ahead in this one, so it'll get a little bit harder to get points towards the end. But as the spec states, if you come down a little ways here, the actual scoring for this is you only need 30 points for full credit, but you can score up to 40 points if you finish all 10 phases of it. And that would earn you a bit of makeup credit here. So if you're looking to patch some mistakes that happened on Project 1, this would be a nice way to do it. Just spend some time grinding there. Problem 2, debugging using GDB in a puzzle-ish fashion. The last problem involves manipulation of a data structure, and it'd be good to start with a picture of said data structure. It's a tree map. Now, if you've never studied tree maps before, then, I mean, I guess what I should say is like you should have hopefully seen a map before at some point in like a 131, 132 kind of setting. And this is just the idea that you have keys that you want to associate with values. Maps themselves are an abstraction, and they're oftentimes backed up with either a tree, as we'll do here, or a hash. There are trade-offs to both approaches. For instance, if you want to be able to visit the items in your map in some sort of sorted order, trees are much favored. If, however, you're looking for the ultimate order one lookup time, then hashes are favored, but you'll lose that ability to do sorted stuff out there. So we'll do trees because we love trees in computer science. And it's good then to keep a picture like this in mind, that each element of this tree is going to have two parts, a key, like L, and a value that's associated with it. The binary search tree property that allows you to say, oh, things less than are left and things greater than are right, they'll be enforced upon the keys themselves because you look up things via their key, and that's where you'd want that sorting order in order to exploit it. So if I was looking up something like Lucas, then I'd look at the root node of the tree and see Lucas as a string sorts after L. Alphabetically, L comes after E does. And so I'll look down here and say at this next node, going right, Lucas, L sorts before M in Mike, and so I should go left. And then check Lucas sorts exactly where Lucas is. I've found the node that I am interested in doing, or interested in finding. I'd return the key associated with it, brash, over here. If I was looking up a key like Hopper, I'd see a similar path, like H sorts after E, H sorts before M, H sorts before L, but there's no child to the left of this, and so Hopper must not be in here in this tree. So any of the things that are in here can be found via that binary search mechanism, and so long as you enforce some sort of mechanism to keep your tree short, which we're not going to do, then you get a log-based lookup here. But the complexity is not a concern. The management is of some more concern. So to demonstrate the basic functionality of the tree, it's good to have an application, and you'll code up this little application, a tree map interactive loop, wherein when you start the application, you will have an empty tree, but then you can add things like L as a key and strange as the value associated with it, Mike as stoic, and then ask like how much stuff is in the tree. You'll notice up here that there's no storage of the size of the tree in here. And so in order to calculate that, you'll probably have to do some sort of traversal on the tree to determine this is how many things are in it. So go through and count how many nodes are in it using a recursive descent. On the other hand, if you wanted to print it out, that would be visiting nodes and then displaying them. And the prescribed order looks sort of like this, where the root is somewhere in the middle here and is not indented, but anything beneath the root is indented some amount corresponding to its depth in the tree. This will make a little bit more sense here after we add a couple more nodes. So let's add Dustin and Lucas into the mix and then print out the tree. L is at the root because that was literally the first thing that was added into the tree. And if you mentally sort of turn your head to the left, you see, oh, L is up the highest here. and to the left is Dustin. So that's just like this thing over here. And to the right of L here is Mike, not indented as much, and to the left of Mike is Lucas. So this prescribed ordering here involves traversing the tree in a sort of, what is it? An in order but reversed order. So first visit the right nodes, and then the left, and then the current node, and then the left node. It'll take a little bit of work to sort of adapt this. It's not a standard tree, but makes for nice visual renditions of the tree over here. So this within this application, then you start to see, oh, there's a main, and the main is going to do things to the tree. So there'll probably be a bunch of functions that do different things to the tree, like add nodes, check if something's in there, compute the size of the tree, and so on and so forth, print it, things like that. There's a corresponding command then that exercises some of those functions, perhaps executing several of them at once there. And if that sounds a little bit familiar, that's by intention, because you'll have implemented a version of this already, or at least contributed to an implementation. Lab 2 featured a list main and list funcs application where you similarly had an interactive loop where adding and checking for things within a linked list instead. And so one of the first steps on the road to victory of this will be to lift as much code as possible from that lab bit and make use of it to get the skeleton, at least for the main, set up for this thing so you can run the tests. Now, further capabilities that you'll need to implement are illustrated throughout this example here. So I encourage you to look at it. And the one that I think is interesting to ponder a little bit is the save and load capability. So you notice here a mention of load stranger.tm. This is a file that is part of the code pack. I think it's actually under the data directory here. So if we jump over yonder and I pop this open, they go into the data directory, there's a stranger.tm. This is the tree here that appears in some of the examples over there. The ordering is a little bit different. It's actually in pre-order. So the first thing that appears in it is the roots, followed by then the immediate children of the roots and their children and so forth along those lines. And this thing is meant specifically to enable you to say, oh, if I read this line and added it to a tree, and then read this line and added to the tree, and read this line and added to the tree, it will exactly recreate some picture of a tree that we had at some point in a program like this, like this one over here. It's a different order than the one that is printed like over here with this sort of nicer visual rendition. But if I added will first, will would be at the root, and that'd be no good because that's the last thing in the alphabet. Everything's going to be to the left of it. So there are a couple different orderings of dealing with things in the tree here. One that's appropriate for printing, one that's appropriate for saving and loading. And the pre-order part of this is good for the saving and loading part. If I remember right, there should be a save command in here. Yeah, okay. So if you save the tree here, this will create a file that has contents that looks something like what we had over there, and allow later on one to reload this stuff so that anything that's lost can be restored from that saved file. And we'll get you thinking a little bit about, oh, if I were writing a program and it had some editing capability to modify and change something, how do I serialize that out into a file that can then restore the state if a user wants to like load or open a file in that way? Many programs, including text editors, have to do something along those lines. And the exact rendition of how you save things doesn't necessarily need to correspond to how they appear in memory in the program or how they're displayed in a program or anything like that. In fact, file formats like that are oftentimes chosen for convenience. What's the easiest way to get out and back in information to recreate such data structures? And this pre-order business of visiting first the root node and then its left and right children and so forth, that's an obvious way to do things with tree data here. Okay, so let's code a little bit on this one so that we're good to go. If you like, you can have a look at the header file, wherein you'll see some of the required structs for the program. There's a tree map node type here that has key and value strings, but then also left and right branches that might be null if there's nothing beneath this on that side, or might point to another node over there. And similarly, then the tree map tree itself is just starts with the root node that's over there. There's a whole bunch of functions that are It's not exactly a requirement, but a suggestion for you to use in implementing. And I'd ask that you do implement all the functions in here because graders will be on the lookout for it. You're free to add to this listing, but as we've done before, I'm actually going to grab this entire outline over here that describes a bunch of tree and other sort of it's tree and node functions that'll become part of this. And these are all supposed to be in tree map funcs.c. So within the code, I'm going to create that file, which doesn't exist, tree map funcs.c, and plop that down. I've already got the pound include of tree map.h of that stuff. And similarly, then I'd want to fill in some sort of dummy initial versions of these functions, although the test cases for this problem, they don't actually test individual functions like this. They test whether or not your main application does stuff right. And so in order to run that, if you were, for instance, going to bop over the shell and type something like make test prob 3, then you need to realize, oh, I actually need a main function for this thing before I could make it. We can make one. So here's a tree map main.c. Then one is sort of left to wonder, like, what should I put in here? Now, here's the first trick to victory. If you remember, I've written something like this before. Go find that something. And you should have worked on something like this before. It will come from lab 2. So let me jump over here and fire up, let's see, my home. Here's 216 in our schedule. Ooh, if I could spell right. Cool, okay. So if you jump over to lab 2, you'll find that there was a similar kind of application down here where, where you insert things into a linked list and ask, is it present, is it not present, etc. How many items in there, stuff like that. Let's grab the code pack for that. Let me copy this link address. I'll jump over here to my shell. I don't want it within the same directory, so let me just change up here. I don't have it here, so let me grab it there. So re-download that thing if you happen to have one that's around already. One's up this thing, and here in lab 2, there's a list main.c. Now, if you look closely, there's a bunch of prints over here. It's like, oh, the linked list demo. Here's what you can do with this thing, and so forth. And this should look sort of like if you come to the top of the example, it's like, oh, look, here's the tree map editor, like the things that you can do with this, and then print a prompt and read that command and do something, then read another command and do something, and so forth. And so this is a direct analog of what we need. So analogous, in fact, that I'm just going to grab the whole thing here and come over to the project directory and make a new file. Oh, wait, I had it up already, tree map main.c. I'm going to paste it all in here. Now, this thing is utterly broken right now because there aren't any lists involved in this case. Rather, there are trees involved. So we'll have to start making some patches to this right away. Like, oh, here's tree map.h, and that's fine. All this stuff about printing lists, that's not necessary right now. We'll have to replace that with what are the tree commands and so forth. There's no list.t, but there is a tree map.t. Actually, let me pull up the header file so I can keep track of that. There's tree map.h down here. It's called, tree map.t. Cool. And at some point, I might actually want to call like a tree map init on this. Well, probably not list. I'll call mine tree map, something like that. Very uncreative, tree map. But since I haven't written the definition for that function yet, maybe I'll comment it out over here. If you look back at the example, there's this little prompt here, tm. Looks like the prompt in the main while loop over here, that's a list. And so I just change this to tm, so it's printing the prompt. I'm going to have to scan commands all the time and check for success or if it's the end of the file, possibly do some echoing. So a lot of this stuff is like built in and pretty good already. Might just start making some adjustments like, oh, the command isn't exit anymore. It's probably something like quit because Kaufman's a jerk and doesn't use the same names like that. So maybe change the string constants and stuff like that. And rather than insert here, it's probably going to be something like, let's see, it's add here. And I have to read instead of one thing to like scan something in, I have to read like a key and value over here. So I might start to add things from there. But I can at least like make a change like this for insertion, or up here, make a change up here to quit instead to see what that looks like. I probably want to change these string constants as well over there. Now I'm going to rifle through quickly here and, well, yeah, and comment out a bunch of the stuff here that will not compile because it has to do with list functions and those just aren't around right now. And this thing, and maybe just say car star ith equals null. That's probably something I'll need to remove later. So list clear, I don't need. List print all, I don't need. And an unknown command, so we'll like clear out this thing. And okay, so now that has excised all of the listy stuff, I think, and left only tree stuff, or limited amount of tree stuff. So let me just look here. List is all commented. List stuff is all commented out. Cool. Okay, so it looks like then we might be able to compile this thing and hit run. Let me change over to my PT code directory. So make test prob 3. I have a unused variable over here. Let's see, what do I do? To fix that, because I definitely want it there. Now I'm just going to comment it out because that's what it'll be. So that'll satisfy the unused variable part. Hey, and I can run the test cases. Look at that. They all fail, but what do you expect? Like, it's a main that does almost nothing, and as well a whole empty regime of different functions that do nothing at all right now. And so to that end, I'd probably do something like, oh, let me uncomment this thing and come back over to my tree map funcs and think about, okay, how would I initialize a tree? Well, there's some advice over here, and it might just be something as simple as like trees root equals null. And now that's no longer an unused variable. And if I look at the main here, like I can actually run this function and it'll be good to go. That I wouldn't expect necessarily to pass any more tests, but hey, the fact that it compiled at all is like I've got something of a working definition for that function. Now you note here, if you actually looked at test cases, and we can do so, and let's pick a mid-range one like test 3 here and have a look at, this is the output file for that. You can see that the tests for this stuff, they don't actually do anything but run your main and feed it a bunch of commands to see if it does the right thing. So left-hand side is what it's supposed to be doing, and right-hand side is what it actually does. Like, it's very confused right now. That means there are no tests of individual functions anymore. And proper unit tests test the unit of under consideration, and that's almost never a function. Rather, the tree data structure, the tree map that we're implementing, that's a unit. To add something into it is fine, but to check if it's in there, you have to use another function like get or print to see if the add was actually successful. And so the unit itself, to maintain internal consistency, you don't want to break the abstraction barrier and climb and say, oh, does this point at the right thing, and so forth. So to ask, like, okay, did the add succeed, you must also print in that way. And this main application does basically that. Like, these first few tests do things like, hey, add grape as a fruit in there, and then print out the tree to see if it looks right for that. I mean, that's not a bad unit test because it maintains the abstraction boundary of there's certain things I can do to this data structure by like put things in and then print it out. And so I'll use those. The internal implementation of it is the business of whoever's writing it. That's all of you. But from the external, it looks okay here in that way. So in that regard, the unit tests here are not exactly going to give you as much insight because a problem with this test could come from the fact that you didn't add right or that you didn't print right. And it's a great debugging exercise for all of you to start to learn, where is the problem actually? Because if I do 3 steps and then look at the results, any one of those steps could be the one that's caused the test to fail. In fact, just printing things out there could cause things to fail because the printing order is wrong in some way. And anybody who sort of associates, oh, unit tests are like a test of any individual function, that's not right. That's missing the point of what a unit actually is. It's too granular at that point. Tests of functions aren't bad, but they're function tests. Then unit tests test data structures or other things that function as a unit, and typically those have some internal consistency that you need to respect. Okay, I'll stop blathering at this point because it's high time for you all to start coding. You can run test cases, you can evaluate results, so that should get you off the ground. You'll need to create the main, you'll need to create the funcs, but after that, the real fun begins. This is project 2, then in a nutshell, a bit level manipulation, a debugging exercise, and a data structure to manipulate. Each of these things is in hand right now, so there's nothing preventing you from getting started, and I encourage you to do so. Deadline is next Friday. That's all I've got for today, and I'll see you soon in lecture. Happy hacking until then.